Hey Ollie, I was reading ahead. They say if vector spaces are the second most important concept in linear algebra, then linear maps are the most important.
That makes sense, I guess. I'm just struggling to get through these notes. They jump right in with a formal definition.
Don't worry, we'll go through it together. It says let V and W be vector spaces over a field F. A map F, V to W, is called a linear map, and then it gives two specific rules.
The first one, L1, is about addition. F of V1 plus V2 equals F of V1 plus F of V2. It's like the function distributes over vector addition.
Exactly. And L2 is for scalar multiplication. F of AV equals A F of V. The scalar just moves outside the function. So a linear map has to respect both of the core operations in a vector space. Put another way, a linear map conserves the structure of vector spaces.
Okay, I think I get those two. It also says if the spaces are the same, V equals W, we call it a linear transformation.
Right. And look, the next page simplifies things even more. It shows we can actually combine those two rules into a single condition.
Oh, I see it. F of A1V1 plus A2V2 equals A1F of V1 plus A2F of V2. This is super convenient. It means we can check both addition and scalar multiplication at the same time.
Exactly. If we can prove this one combined property holds, we've shown it's a linear map. It's a nice little shortcut for proofs. Let's look at the examples. The first one is f of x equals 2x from R to R. Do you think it works?
I think so. Let's test it. For addition, f of x plus y equals 2 times x plus y, which is 2x plus 2y. And f of x plus f of y equals 2x plus 2y. So L1 holds.
Perfect. And for scalar multiplication?
F of ax equals 2 times ax, which is a times 2x. And af of x equals a times 2x. So L2 holds too. Okay, yeah, it's a linear map. That one was straightforward.
See, you got it. But the second example, f of x equals 2x minus 1, is not. I can see why. The minus 1 is a constant term, and it breaks the rules.
Let's check it just to be sure. F of x plus y equals 2 times x plus y minus 1, which is 2x plus 2y minus 1. But f of x plus f of y equals 2x minus 1 plus 2y minus 1, which is 2x plus 2y minus 2. Those are definitely not the same, so L1 fails, and it's not a linear map.
This next point is a good sanity check for us. Any linear map has to take the zero vector to the zero vector. F of 0v equals 0w. If a function doesn't do that, we know it can't be a linear map.
And the proof is right there. It uses L2, setting the scalar a to 0. F of 0v equals f of 0v equals 0f of v equals 0w. It's a nice simple proof.
Okay, theorem 1 is interesting. It says that for any matrix A, the map F, A of V equals AV is a linear map. That means every matrix is basically a linear map.
That's a huge takeaway. I hadn't thought about it that way.
The proof on the next page uses the properties of matrix multiplication that we already know. It just applies the combined linearity condition. A of A1V1 plus A2V2 can be split up into A1 times AV1 plus A2 times AV2.
So the linearity of the map is a direct result of how matrix operations work. That's pretty cool.
Theorem 2 is about function composition. If you have a linear map f from v to w and another linear map g from w to u, then their composition, g after f, is also a linear map.
That makes intuitive sense. If you apply one linear operation and then another, the total result should still be linear. The proof on the page just shows that by applying the linearity of f and then the linearity of g.
Here's another important one, Theorem 3. If a linear map f has an inverse, then its inverse, F inverse, is also a linear map.
That's not obvious. How do they prove that?
Look at the proof. It starts by defining V1 and V2 as the inverse images of W1 and W2. Then it uses the fact that F is linear to get a key step. F of A1V1 plus A2V2 equals A1W1 plus A2W2.
Right. Then it just applies F inverse to both sides of that equation, and you get the linearity condition for F inverse. That's a clever way to do it.
And that brings us to the main event, isomorphisms. An isomorphism is just a linear map that's also
Bijective, which means it's both injective, one-to-one, and surjective, onto, right? I remember those terms from another class.
Yep. And when two vector spaces have an isomorphism between them, they're called isomorphic. The notation is V is isomorphic to W. The notes say they're indistinguishable from a linear operations perspective, which is a big idea. So let's look at this last example to see it in action. We have a subspace W of R2 defined by the equation 2x minus y equals 0. And we have a map FA from R to R2.
The first step is to show that the map's output actually lands in W. The output of f of a of x is a vector x, 2x. If we plug that into the equation for W, we get 2 times x minus 2x equals 0. So it works. The image of the map is a subset of W.
Now we have to show it's an isomorphism, which means proving it's surjective and injective. Surjective first.
It shows that any element in W can be written in the form of x, 2x. That's the exact form of our map's output. So for any vector in W, there's an input from R that produces it. It's surjective.
And for injective, it assumes two different inputs give the same output. F of a of x equals f of a of x prime. That means x 2x equals x prime 2x prime. The only way for those vectors to be equal is if x equals x prime. So the inputs must have been the same to begin with. It's injective.
Since it's both surjective and injective, it's bijective. And since it's also a linear map, it's an isomorphism. The conclusion is that R and W are isomorphic. They are structurally the same.
See? That wasn't so bad. That's a great example to tie everything together. I think I've got it now. The notes make a lot more sense after breaking them down like this.
You're right. I feel much better about it now. What do you think we should tackle next?
How about we look for some practice problems on isomorphisms? It'll help solidify the concepts we just went over. We can revisit the proofs later if we get stuck.
Sounds like a plan. Thanks, Hana.
Anytime, Ollie. Let's get to it.